Optimization is the calculus AB topic of finding the minimum or maximum value that a function can take on an interval. It can be applied to real-world scenarios easily. There has to be one quantity that the reader is interested in and another condition or constraint that restricts the value in some way. Some scenarios that optimization can come handy in real life is maximizing/minimizing area, volume, population, and perimeter. When being applied to real-world scenarios, the question will be in paragraph format, so it's important to understand which variable you're trying to optimize. There are three methods in finding the solution to an optimization question. The first method is finding the extreme values of the function on the interval to find the minimum or maximum. The one drawback of this is that sometimes there isn't a closed interval, and perhaps when you differentiate the function isn't continuous. The second method is using the first derivative test. With this method, you would solve for any critical values of the function and find when the derivative function is positive and negative. Using the fact that the function is increasing when the derivative is positive and that the function is decreasing when the derivative is negative, the solution can be found. The third method is using the second derivative test. With this method, you would find the second derivative and the critical points of the function. If the second derivative is positive at that critical point, then there's a relative minimum, and if the second derivative is negative at that point, then there's a relative maximum. So this is our first example problem. The question reads, suppose you had 100 meters of fencing to make two equal side-by-side enclosures as shown below. What is the maximum area that you could enclose? So over here I drew a little picture, and these are meant to be two side-by-side equal enclosures. So first let's give them variables. Okay, so let's make the y the height, so they're all equal, and x is the length. X, and x. Okay, so what does area equal? Area for both of the enclosures together equals 2x y, right? Because it equals xy plus xy. And the perimeter would be, how many x's are there? There's 4 x's and 3 y's. So it becomes 4x plus 3y, which also equals 100 meters as is the constraint in the problem. So let's write that again. 4x plus 3y equals 100. And in order to solve optimization problems, we want to get the problem in terms of one variable. Okay. We want to get one of the equations in terms of one variable, so you could substitute in the other to maximize it. Okay, so let's solve in terms of x. 4x equals 100 minus 3y. X equals 100 minus 3y all over 4. Okay, and let's plug this into the area equation. Area equals 2x y. Area equals 2 times 100 minus 3y over 4 times y. Alright, and over here you can cancel this, get a 2 here. Area equals, let's see if I can distribute this straight up, 50y minus, and 3y over 2 is the same thing as 1.5y, so 1.5y squared. Alright, and so what we want to do is try to find the critical points of this function. So critical points occur when the derivative of the function equals 0 or undefined. So when does a prime equal 0? First we'd have to find a prime. A prime equals 50 minus 3y. So what we did there is we differentiated in terms of y. So if we solve for 0 equals 50 minus 3y, y would equal 16.6 repeated, which is roughly 16.667. All right. Okay, so we found the y, and we have to test this to make sure that's actually a critical point. So to make sure that's actually the absolute maximum. So we can use the first derivative test. So what does the first derivative test state? The first derivative test says that if the derivative function goes from positive to negative, that means the function has an absolute maximum. And if the derivative function goes from negative to positive, that means the function has an absolute minimum. So a prime, and we can draw a little number line over there, and there's only one critical point, 16.66. So any value before 16.66, if we plug it into this equation, then it would be positive. Any value more, the function would be negative. And that indicates that there is only one absolute maximum, and that's the value. So we found the value of y, right? Now we can find the value of x. So 4x plus 3y equals 100. 4x, let's plug in the 16.66 repeated, plus 3, 16.6 equals 100. Cool. So 4x equals 100 minus 3 times 16.6 repeated. So x equals 12.5 meters. And I can write that over there too, meters. Okay, so over here we have the dimensions, not the dimensions, we have what x and y equal. So the question asks us to find the maximum area. And area equals 2xy equals 2 times 12.5 times 16.667. And if I plug that into my calculator real quick, we get 416.667. It's asked for area, so that becomes meters squared. All right, there we have it. That's the solution to the problem. So now we've reached the second problem. This question reads, a company that specializes in creating containers wants to create a new product. The engineers at the firm are tasked with creating an open box with a square base and a surface area of 250 square inches. With those conditions, what is the maximum value that the container can have? So over here, I took the liberty of creating what the figure would look like. So essentially, it's a rectangular prism with an open top. And I shaded the top to show that's open. And so what that means is that there's 5 sides to this rectangular prism. So let me label the variables first. Y, I'm making the y the height. Y, this side's also y. X, and x. The base is square, so that means x, both sides of the base are x. So volume equals x squared times y. And the volume of any prism would equal the volume of the base times the height of the prism. And so now let's find the volume of the formula for the surface area. That equals x squared for the base plus 4xy, since there's 4 sides around it. Okay, that's what we have up there. And that also equals 250 inches squared. So now let's solve for one of the variables. It's easy to isolate y in this, so let's solve for y. 4xy equals 250 minus x squared. Y equals 250 minus x squared over 4x. All right. So now let's plug this into the volume equation. Volume equals x squared times 250 minus x squared over 4x. Volume equals, and we can cancel that, and we can distribute this as well. So 250x minus x cubed all over 4. volume equals 250 over 4 is 62.5x minus 0.25x cubed. All right, so now let's find the critical points. The critical points can occur when the when the derivative of the function equals 0 or undefined. In this, the function can't equal undefined, so let's find when the derivative equals 0. So the derivative equation would be 62.5 minus 0.75x squared. So if I plug this into the calculator, I can solve for when v prime equals 0. Okay, that would occur when x equals 9.129, and that's in inches. All right. And now we want to show that this is the absolute maximum. All right, so we can use a second derivative test to prove this. So v double prime equals negative 1.5x. And that's using this equation here. If we take another derivative of that, using the power rule, it would become negative 1.5x. And now, as we see here, since x always has to be positive, since a unit of measurement can't be negative, that means this function on its interval, it's always negative. So using the second derivative test, always negative. So now we can use a second derivative test to state that since the second derivative is negative at the critical point, which is 9.129, that means the function has a absolute maximum when x equals 9.129 inches. Okay, so what does the question ask us to find? It asks us to find the maximum volume of the total container. So we found x is 9.129, so now let's find y. Volume equals x squared y. Nope, we can't use that equation for it. We have to use the surface area equation. So y equals 250 minus x squared over 4x. X squared over 4x. So if I plug this in the equation, equals 250 minus 9.129 squared over 9.129. Cool. So y equals 18.257 inches. And now we would need the volume equation. So volume equals x squared y. X equals 9.129. Volume equals 9.129 squared times 18.257. This equals, and if I plug this in the calculator, that would equal 1521.451. 4.5. Actually, this is a 2 inches cubed. It's volume. All right, so there we have it. That's the second example problem solved.